are going to go over the E fields of conductors and insulators. All right, let's begin. So let's start off with conductors. So one of the things that I want us to keep in mind is that conductors allow for negative charges to move freely. Okay, so that's going to be a very common thing that we're going to remind ourselves over and over again. See negative charges. So as infantile as this analogy might seem, I think it does a really good job of thinking about what exactly is happening during the charging phases of conductors. So in my analogy, I said, so imagine like you have like free class time, or class time, you're not bound by your seats, you're allowed to move anywhere, and someone passes gas. Okay, so you are the negative charges. What are you gonna do? And I'm not just talking about like your everyday passing gas. I'm talking about like the really, really bad stuff. Okay, so as horrible as it is going to be for that one person that passed the gas, everyone's going to be as far away from that one person as possible. Okay, so you are the negative charges, and you want to be as far away from everyone else as possible, right? You're like you're pressed up against the walls. So let's now consider that idea, that analogy, with other objects such as metals. So metals are conductors. How would these negative excess charges act? So now that we have that analogy there, let's do a quick little sketch. So if we have, it doesn't matter if it's a hollow charge or a solid charge. Let's say we have a metallic object or metallic sphere, and we deposit on that sphere, let's say a couple of negative charges right towards the middle. So here's the important thing: because charges can freely move, okay. The negative charges here will be as far away as possible. And this is because of Coulomb's law, right? And so this negative charge here is going to push against this negative charge, which is going to push against this negative charge, which is going to push against this negative charge. And so what ends up happening is that you have a metal sphere where the exterior has all of the negative charges, okay? And the negative charges are as far away as possible. Now, if we were to take a look at this chunk of the sphere, right, the innermost part of the sphere, the important thing is that there are no negative charges there. Okay, all the exit charges are always on the outside. So, what if we were to deposit a negative charge right there? What would happen? Well, all the negative charges surrounding that newly added negative charge will push it away so that it is as far away from the others as much as possible. All right. Now, with that being said, now we have to think about this idea of electric fields. Okay. So we know that the electric field is, let's see, is equal to kq over r squared. So we have the E field formula. So if we were to think about this, right, what is the electric field within here? Well, if we take a look at the formula for what it is saying, it's saying that if we were to take a look at that chunk of the conductor, okay, how much excess charge do we have there, or how much charge do we have there? And because we're looking at this metal sphere almost like a point charge, so instead of, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, so instead of taking a look at this as negative 11 individual negative charges, we are like viewing it as just a singular object with a negative 11 coulombs, right? And so if we're taking a look at like a zoomed in view of it and looking at that portion, we can say that in that zoomed in portion there are no excess negative charges. And the question is why? Why aren't they? Well, we just went over it, right? Because they're all on the outside. And so the E field within here is actually 0 newtons per coulomb. Okay, and what if we were to expand our view? Well, even if we expand our view, the closer we get out, because there's still no excess charge there, right? There's no charge there. There's no E field. And it's not until you actually get to the outermost surface where there are excess charges, and it's not until you actually get to the outermost surface of this system where the E field actually exists. And so, if we were to create a diagram By the way, this idea here, this is what we call a Faraday cage, and this is the same idea as a Van de Graaff generator that we will be using in class. So for a Van de Graaff generator, inside the generator, it's hollow, and so there's no E fields there, and that's that's fine and all that. But the important thing is that negative charges are all on the outside of the Van de Graaff generator. So when you touch the outside of the Van de Graaff generator, right, that's when you get that shock. But there's nothing happening within the interior of the Van de Graaff generator. All right. So if we were to take a look at the E field versus the radius, okay, let's say that the radius of the actual sphere here, okay, let's say the actual radius of the sphere from here to here is a capital R, and anything up until, right, that capital R, we can say this is like lowercase r. So in this case here, from up until that capital R, we say that our E field is actually a big fat 0. But what if your R equals R? So when your R equals R, if we were to take a look at the E field formula and the relationships, we know that it's inverse square proportionality. So when we are at R, we have the greatest amount of E field. And so the E field actually shoots up to its maximum amount. Okay, and so now we're looking at the R when R is equal to R, and then as we go beyond where R equals to R, as we get further and further and further out, our E field weakens. And we discussed this when we're talking about how to draw E fields. Remember, when we're drawing E fields, we're always thinking to ourselves, okay, so if we were to just do a quick E field vector diagram, right? These vectors are a combination of the E fields surrounding this charge. And the idea is when we are here, the E field is super strong, but when we're out there, the E field is super weak. So if I were to draw the E field of this furthest point, I would draw it like pretty tiny. But let's say I were to draw the E field closer to the charge itself. I'll do this in a different color, right? But I would draw it like this, nice and big, right? A lot bigger than that tiny E field I drew before. Okay, so we have that inverse proportionality. Okay, well, now that we talked about conductors, what about insulators? So insulators, we're going with the same analogy. I think it works well. So let's say we have a similar scenario, except it's not like free time during class where you're free to move around, but you're like in the middle of the SATs or like super important exam, and no matter what, you cannot leave your seat. Okay, and so this is the idea of insulators. Insulators like to hold on to the charges as much as possible, and the insulators say, you're not getting anywhere. Okay, there might be a little bit of polarization that occurs, but other than that polarization, that charge is not free to leave. You are bound to your location. So kind of like if we have the same idea. Let's say the stinky gas was released here, right? Everyone is going to be kind of like leaning away from that region. So the closer you are to that region, right, the more polarized you're going to be, kind of like this, right? You're going to be like leaning away. The negative charges are like, ooh, getting away. But the further away you are, right, the negative charges aren't going to be leaning away as much because they're more or less bound to their current location, right? So this one you can see a clear polarization, right, because it's like leaning far away, but here you can see a tiny amount of polarization because the closer you are to the source, right, there's going to be more of an effect of a polarization. Okay, so let's use the same idea here of trying to figure out what the E field would look like. So in future units, we're going to go over the math as to why this is the case, but let's go over the general ideas. So if we were to come up with a E field versus R effect, okay, we're actually going to work backwards. So if we are outside of the charge and we're looking at, okay, what we're seeing is a net overall point charge. And so we know that the net overall point charge, so let's say at this point we have R, anything beyond that, according to the E field formula, anything beyond that will still follow the inverse square law, just like that. But as we shrink this this circular perimeter and we get closer and closer in. So for example, I'm going to use this color here. Let's say we look at this perimeter, okay? Um, and if we were to verse that circle versus, let's say, a tinier circle, let's do this in purple, let's say a tinier circle, what we're essentially doing is we're looking at chunks of the insulator. And so the more amount of chunk that you see, the more charges you see. And so if the more charges you see, that equates to a more of a E field, because we know that is KQ over R squared. So the bigger this spherical chunk, our Q goes up. And so if we're shrinking that chunk, our Q goes down. And because E and Q are directly proportional, okay, and it's a linear proportionality here, what we get is this really cool effect where the E field, as you expand out from the very middle of the charge, okay, to the very outside perimeter of that insulating object, we get a linear relationship. So here we can say that E is directly proportional to the radius. Okay, but over here we get E is inverse square proportional to the radius. And once again, in our next unit, we're going to look at the specifics as to why that is the case, thanks to the use of calculus and math. All right, that's that. I'll see you next time. Bye bye.